Allen. I'm the partner. Alright, good morning everyone. My name is Noel Allen. I'm a part of Team 5, along with my teammates Turnier and Mojica. Today our team will be discussing our proposed design project idea, the modular upper limb prosthetic for children. Now, in the United States, about 1.7 million people live with limb loss. About 33% of all pediatric limb amputations are caused by trauma or disease. Trauma accounts for the majority of upper limb amputations. In fact, trauma when compared to disease-related amputation occurs twice more frequently in the upper limb region than the lower limb region. Now, for our prosthetic, our target age range will be children between the ages of 5 and 12 years old. Now, on to our motivation and goals. Prosthetics in general are extremely expensive, especially considering that our prosthetic is geared towards children who are in a time in their lives where they're constantly experiencing growth. Now, this makes it extremely difficult for their parents who want their child to have a functional prosthetic, but won't be able to financially compensate for the constant replacement of the prosthetic to accommodate their child's growth. Now, this leads into our first goal, which is to increase useful life. The way we plan to tackle this is by first dividing our initial age group of 5 to 12 years old into two sections, 5 to 8 years old, and then 9 to 12 years old. This is because the limb difference between 5 to 12 years old is too large of a gap to be feasible enough for us to incorporate trackability. Now, if we look at the table, we can see from 5 to 8 years old, there's about 4 centimeters of limb difference. Now, comparing that to 5 to 12 years old, there's about 10 to 12 centimeters of limb difference. Now, looking at the both age group, that's about 3 times the difference in limb. Now, on to how we plan to reduce our costs. In our engineering design and analysis, our goal is to develop a sound prosthetic using the most optimal and also the most cost-effective material. We plan to couple this with a cost-effective fabrication process. Now, on to our last goal, which is to implement modularity. We refer to modularity in the sense that if the device were to be damaged in a certain region, that region could be directly disconnected and serviced instead of having the entire prosthetic device replaced. Now, tying into our curriculum, a major part of our project is to make a global impact. The majority of prosthetics on the market that we observe have not been readily available to those who are really needed in third world countries. In our research, we crossed over the fact that in India it's been recorded per year that there's about 17,000 or more amputees that lack a functional prosthetic. Now, the way our team plans to engage the global community is by making our prosthetic with readily available material, and also we plan to open source the prosthetic and also provide ease of fabrication. Now, up next will be Finley to delve a little bit further into our project.
Now, taking on this project, there's several challenges that we have to be prepared to encounter. Most of these challenges are human factor considerations under the category of comfort, functionality, and adaptability. Comfort as far as how willing is an amputee, how willing are they to bear a prosthetic through an entire day? Functionality, how much does the prosthetic enable them to carry out everyday function, everyday tasks? And adaptability as far as how intuitive it is to actually adjust a prosthetic as the child is growing. Now, another major challenge is to reduce the causes of abandonment. Our main focus is on transradial level amputations because the majority of amputees are transradial level amputations, and it's 54% overall in the general body of amputees. Causes of rejection include skin irritation, body pain, and a lot of causes of rejection include discomfort, weight, technology, and appearance. As you can see, among both rejectors and wearers, the percentages are pretty high. So even for wearers, they find that sometimes prosthetics are just not, they don't enable them enough to actually bear it throughout the whole day. Now, we plan on breaking down the project into 2 phases. Phase 1 is pretty much to design and make the solid prosthetic. And then we'll proceed into the engineering analysis, where we delve into finding the appropriate materials to fabricate this prosthetic, and then try to see what the physical limitations are with the prosthetic as far as being able to withstand the weights or bearings on the prosthetic body. And then we want to optimize the design. Our phase 2 is an additive stage where we plan to develop a terminal device and then add driving mechanisms to pretty much add functionality to the prosthetic. And then we plan on trying to delve into developing the actual prosthetic controls between the amputee and prosthetic. Now, the relevant standards that we plan on pretty much implementing pretty much we have to abide by the regulations set by the FDA. On the system level, the FDA is pretty much the general body that pretty much regulates whether a prosthetic can be brought out to the market. On the component level, we have a variety of standards that we have to meet. American Society of Mechanical Engineers, AS, American Society of Testing and Materials. These are more like related to components and how actually create a prosthetic and deal with the stresses and actual overall engineering analysis of the device. Among these standards, some of them are pretty much created by two bodies. For example, these are some of the listings of requirements that we have to apply. One of the key factors here is general requirements for safety and essential performance. Usability specification is important. Usability engineering process, usability in the engineering process. How much is a prosthetic actually functional, and how does it assist a person throughout their everyday lives? And then our main purpose is pretty much the human factors engineering extended to all devices with emphasis of risk management and life cycle. We have to pretty much make sure the device is functional and pretty much does not cause any harm, and pretty much enables a person and implements the task as it's supposed to. Now, Chris will delve into our alternatives.
First design alternative that will be considered will be the socket. The socket is known to be one of the most important parts of the prosthetic itself. In order to produce a suitable socket that fits well over the residual limb, it will minimize discomfort and increase functionality. Examples of such attachments related to the socket itself include silicone suspension, locking suspension, and osseointegration. Silicone suspension deals with rolling a silicone liner over the residual limb, creating a seal. From there, a pin will be connected to the socket itself, and then from there, attachment will be created between the socket and the prosthetic arm itself. However, due to material that is used into this type of method, it has caused hyperhidrosis, skin irritation, and has proven to have poor thermal conductivity. Bachmann suspension deals with creating a negative pressure between the socket walls and the residual limb itself. In doing this, it prevents motion between them both. However, in this method, there is high pressure from the vacuum itself. This high pressure creates heavy perspiration, and then combining this heavy perspiration with shear forces causes pressure ulcers. Osseointegration deals with implanting a titanium plate directly to the residual limb's bone. From there, a pin will be screwed onto the titanium plate. From there, attachment of the prosthetic to the pin will be available. However, due to this material, bone and skin infection has occurred. After evaluating a range of different sockets, the ideal socket that we chose was the Wilmer open socket. We chose this socket based on the fact that it was originally designed for children having transradial amputation. This socket weighs between 100 grams and 200 grams. Advantages of this socket include that it is adjustable, perspiration is minimum due to the fact that 75% of the skin is uncovered, and it is easy for donning and doffing. Concerns related to the socket from users include that it is too bulky, it's not appealing, and users would like a more closer interaction between the socket and the residual limb. Therefore, instead of using a soft foam that is currently surrounded around the stainless steel pipes of the socket, we will use a cross-woven spacer fabric. This will not only reduce the bulkiness, but it will also create a close interaction between the residual limb and the socket itself. This fabric has the ability to absorb moisture, to transport moisture and heat as well, and it is also washable. The second design alternative that we considered will be the wrist. And having an option to incorporate a wrist and not incorporate a wrist will play a key component in depicting its functionality and complexity of the prosthetic arm itself. In having a wrist, it will not only optimize the prosthetic arm and increase its functionality, but it would improve its range of motion, creating a human-like range of motion between the socket wall and the hand itself. Here's a preliminary design of the socket of the prosthetic arm that we plan on creating. Thank you. Any questions?
I have a comment on your follow-up when you do present this. Put things in black, write all your letters in black. It's very hard to read from here. If you go back a couple, you can read it from where you're standing, but up here, it's very difficult to read some of your smaller thing. So I make them in black, leave the blue background, but make them in black. Second comment is, or question is, what kind of engineering are you using to develop this prosthetic? Is this going to be electric? Is it going to be mechanical? How is the person going to operate the fingers and the operational part of this?
So the first, phase one, was first pretty much dealing with the mechanical side of creating a prosthetic. Pretty much making it be able to withstand the weight of a human being, because that's one of the standards they pretty much established as far as making prosthetics. And then added stage, the second phase is actually adding those mechanical driving elements. And what we want to do is we want to delve into a myoelectric type of prosthetic. What that means is that it will be driven electrically by taking pretty much signals from the residual limb and driving the pretty much DC motors. So we want to add DC motors into the cavity of the hand, which will drive the, in effect, is the fingers.
You haven't got too far along on that yet.
Okay, so you want to
Am
know?
I guessing that's right?
Yeah, I mean, it's pretty much, so you're asking how will it be driven? Like how will it function? We want to delve into adding electrical motors into the cavity of the hand that will drive the fingers. So it'll be an electrical system, pretty much. An electrical system that takes impulses from residual limb. We found open source circuitry to actually read pulses from the residual limb that we can use to translate signals to the DC motors.
Okay, then, as I grow up, you're going to take one of those sections and enlarge it so you can still use the hand
Yes.
and the part that would grab your arm and add a piece in the middle. Is that the concept?
Yeah, so the concept is pretty much, this piece right here, we plan on layering this with the appropriate material to pretty much block this cavity. But what happens is that as the child grows between those two stages, between 5 and 8 years old, this part will be able to adjust. The hand, we've got the anthropometric data, and we would say that, okay, between 5 and 8, we know the general size of children's hands. So we'll pretty much design it to be in between area, and then keep the hand, but this will be considerably be able to adjust for that age range of 5 to 8. So this portion right here. So it'll have a mechanism in here to adjust accordingly.
Now, do you have any idea how much it would cost to produce that?
Well, okay, we want to try to find the cheapest. I mean, the cheapest and most reasonable means of producing the prosthetic. 3D printing, as of right now, seems like a good way to go, but it depends on how much, realistically, a 3D printed prosthetic, how feasible is a 3D printed prosthetic as far as being able to take loads. That's one challenge that we're seeing. The higher quality 3D printing, the better strength we're going to get into the overall product, but the lower quality, the more brittle and fragile the prosthetic will be. So it's kind of like a balance. So the higher strength we get, the more cost it'll. But we're trying to shoot under around $1,500 because we know implementing a myoelectric system by itself costs $500.
Looking at your project, phase 1 is enough of a project. Phase 2 is, to execute phase 1 right is a good project. So my guidance to you would be to step off of phase 2 completely, because I don't know how, first thing, your design should be done now. You don't have a design for the phase 2 phase at this point, correct?
No, we don't have an established idea yet because
Okay.
we're still trying to.
And to be able to use the prosthesis for example, all the amputees in India, if you start putting motors and mechanisms in there, it's not going to work. And your price will go too high. To make an arm, a prosthesis that actually functions, where you can position it, you can hold a bottle, yet do it mechanically, would make more sense to me. And to put a lot of good work into adjustability of the design. I mean, I can envision you putting a thread on that thing and having the ability to adjust it and lock it down, for example. That's my feedback.
Yes, yes. We'll take that into consideration. That's why we've said phase 2, we're pretty much saying it's an additive stage, because we're still pretty much trying to set.
But where I'm going with it is make a decision on that,
Okay.
because that in itself is a project.
Yeah. Understand. Okay, we'll consider that.
Yeah, we're gonna look at you again come May. You're gonna look at the same faces out here.
Yeah. Okay, thank you. Any more questions?
Thank you.
I think Dr. Tomanto's suggestion is right on, as we also discussed earlier. Finley has a attachment passion for some reason to create a mechanical hand with 5 fingers, which I couldn't persuade him to get out of. But what Dr. Tomanto really says makes a lot of sense to mechanically make it a functional and modular system is going to be very valuable and more doable actually, because at the end of this next semester you can come up with something that doesn't work at all with so many actuators, so many degrees of freedom in 5 fingers. Just controlling that itself will be a big challenge. So I really think we should pay attention to Dr. Tomanto's suggestion. Any other comments? Thank you very much.